So it's my pleasure to introduce Professor Thomas Griffiths. Professor Griffiths has published in many top journals, including Science and Nature. Among many others, he has received John Simon Guggenheim Memorial Fellowship, Foundation Fellowship, an award given, I am citing here, on the basis of prior achievement and exceptional promise. He has also co-authored the book Algorithms to Live By, and even managed to write a manifest for a new computational cognitive revolution. On a personal note, I can say that there is a lot of things to envy about him, because for us, the young scholars, he is so young and so well achieved. So we have to learn from you the secret of achieving so much at such a young age. So the talk will proceed as follows. Now you have about 45 to 50 minutes for your presentation, and then about 10 minutes for 15 minutes for questions. And then those who have to go will go. And if it's fine with you, you will stay for another 15, 20 minutes for additional discussion. So if it's fine, the floor is yours.
Great, sounds good. And thanks for having me virtually here. I really enjoy following the work from your group, and so it's nice to have the chance to talk to you. So what I'm going to talk about today is joint work with Falk Lieder, who was a graduate student with me at Berkeley, and is now, after having been at the Max Planck Institute, on his way to be a faculty member at UCLA, and then Fred Calloway, who is a graduate student here at Princeton and is on his way to NYU. So as you can see from my affiliation here, I'm in two departments, the Department of Psychology and the Department of Computer Science. And in some ways, that gives me sort of two different perspectives on human minds, right? So, when I am in the psychology department, what I learn is that humans are kind of embarrassing, right? If you ask psychologists about human decision-making, you find out all these things, like we're predictably irrational, where mistakes of reason rule our minds, our reasoning is fallible, our brains are kludges, right? So this kind of idea that the way that we go about making decisions is sort of a consequence of error-prone heuristics that result in systematic biases that have negative consequences for our behavior. But if I walk across campus and talk to my colleagues in computer science, I get a very different perspective. So for the computer scientists, humans are inspiring, right? So, we want to build computer systems that are able to do the kinds of things that human beings are able to do. In many cases, humans are the best example we have of systems that are capable of solving certain kinds of problems. And this is just one example from the history of artificial intelligence. So this is Garry Kasparov playing chess with the computer Deep Blue. So in this, particular situation, the computer ended up winning, right? This is the first time that the AI systems defeated a world champion in chess. But in some ways, if you want to sort of be re-inspired by this, it's worth pointing out that this wasn't a fair contest. So, on the right, you have a system that's capable of searching about 100,000 chess positions per second, whereas on the left, you have a system that's capable of searching, at least in can everybody see the slides? There's just a chat question about it.
I can see them fine.
Okay.
Yes, you're still on the Kasparov page, right?
Yeah. Okay, good. All right. So, explicitly searching about one position per second. On the right, you have a system that's powered by an industrial power plant. On the left, you have a system that's powered by some black coffee and a piece of toast, right? So there's a big difference in the efficiency of these systems. And so if we want to be re-inspired by humans, we can look not just at all of the kinds of things that human beings can do, but also the fact that we're able to do all of those things with about 2 pounds of neurons, that and being powered by this sort of very efficient use of some biological matter, right? And so we still haven't made any system that parallels that kind of efficiency. So these two perspectives on human minds set up a bit of a paradox, right? Are we smart or are we dumb? Are we, are we inspiring or are we embarrassing? And I think we can resolve that paradox to some extent by recognizing two things. First of all, that we have limited cognitive resources. That's something that leads us to make errors in decision making. This isn't a new insight. This is something that goes all the way back to Herbert Simon in the 1950s, sort of pointing out this idea of bounded rationality. But also that we do a good job of using those resources. So what makes us smart, what allows us to succeed in doing all of the different kinds of things that we do, despite having those limitations, is that we're masters of using limited cognitive resources effectively. And so that's what I'm going to focus on in this talk, is the second part, just trying to characterize how you would even determine that, what it means to use cognitive resources effectively. And in the process, we're going to go back and we're going to actually reconsider how it is that we define rational action. And so the standard way that we define rational action, and the sort of standard that's used for comparing people against, that leads us to then conclude that people do things that are dumb and embarrassing, is the standard of expected utility theory, right? Where the idea is that what we're going to do is take the action that maximizes expected utility. Our maximization here is over actions. And this expectation is taken over a probability distribution of possible outcomes that are associated with those actions. And so if we reduce this to a slogan, the slogan is something like do the right thing, right? It's sort of putting the emphasis on the action that we take in the environment that we're in. But it's worth pointing out that there are a few things that are unsatisfying about this, right? So first of all, it says nothing about the computational resources that might be required to choose that action, right? It just says choose the best action, evaluate expected utility, not recognizing that evaluating expected utility itself might be an extremely computationally costly operation, right? And that there may be circumstances where it would take us forever, or it might even be uncomputable to work out, what the expected utility of an action might be. The other is that if we are interested in what goes on inside human heads, this kind of standard is a very limiting standard, because it only talks about the environment that we're in and the action that we take in that environment. And so from this perspective, this is a kind of behaviorist theory of rational action. It's one that is just about actions and environments, and says nothing about cognitive processes. So there's another way that people have started to think about rationality, which comes from the literature in artificial intelligence in the 1980s, where AI researchers started to think about, if we're going to build AI systems, what are the goals that we should have for those AI systems? What's the objective that those AI systems should be trying to fulfill? And so they proposed an alternative. It's gone under various names: bounded optimality, computational rationality. We talk about resource rationality in terms of the idea of making use of cognitive resources in general in a way which is efficient. But roughly the idea is that what we should be focusing on, rather than putting our emphasis on this external action, is the internal processes that we execute in order to select those actions in the world. And so here the emphasis is put on the strategy that we're going to use in terms of trading off utility and computational cost. And so our sort of outer maximization here is over strategies or policies or algorithms that we're going to use. And what an algorithm consists of is a sequence of computations, each of which changes the beliefs that we have about the world and is associated with some underlying cost, such that having executed that sequence of computations, we get to a point where we have some beliefs that are then informative in guiding the action that we end up selecting. And so what we're going to do is we're going to then choose the action that maximizes expected utility, subject to the beliefs that we've obtained as a consequence of the computations that we've executed. And so if we reduce this to a slogan, that slogan is something like, you should do the right thinking, right? It puts the emphasis on what's going on inside our heads, rather than on what it is that we're doing in the external world. And so if I reduce this even further to a cartoon, put something like this, right? Here's expected utility theory, just about the action we take in the external world. Here's resource rationality. We're putting the emphasis on the computations we execute inside our heads that then guide us in selecting those external actions. And so the idea here is that this gives us a different way of thinking about, what it is to be rational agent, but also a way of thinking about how we should be using those internal cognitive resources. And now that gives us a tool that we can use for reconciling those two different views of the mind, because a lot of the things that we do that seem strange and maybe embarrassing are things that we can make sense of with respect to this kind of perspective. So when you take into account the cost of computation, the kinds of heuristics that people seem to follow that result in systematic biases are resource rational in the sense that those biases are worth it, given the savings that we get in computation, right? If you think about what the definition of a heuristic is a strategy that we can follow that reduces the effort we have to expend without significantly reducing the performance that we get at the end of the day. It's a good trade-off between these two things of how well we do and how hard we have to think. So I'm not going to talk more about these particular examples today. If you have questions, I can sort of go through them in the questions. I'm going to focus on a slightly different problem because there's a sense in which these results are sort of easier to get because we knew already what the heuristics were, right? And so now we're using the framework to go back and we can explain, okay, these things that people do that seem strange maybe make kind of sense. But there's another problem that we'd like to be able to solve, which is being able to say what kinds of heuristics or what kinds of strategies we expect people to follow in a new situation. And so this in general is a challenge for the heuristics and biases approach to understanding decision-making, right? As a consequence of a lot of industry by economists and psychologists, we have a long list of heuristics that people might be following. But then if you put people in a new situation, you have to make predictions about what kind of heuristic they might use in that situation. And we don't necessarily have good tools for answering those kinds of questions. And so what I'm going to do is try and engage with those kinds of questions, but doing this in a way where we set the problem up as one of deriving what the optimal strategies would be given a particular situation that we face. And the goal here is to have a sort of fully generalizable theory that allows us to make predictions about the kinds of strategies people will follow in a wide range of situations. So the strategy here for solving this problem is to go back to this way that I defined resource rationality, and to recognize that really this problem becomes one of making choices about the internal computations that you're going to execute, where this formula gives us a characterization of what the sort of trade-offs are that we're manifesting in making those choices. And when you start thinking in these terms, where we're thinking about the elementary computations that we might execute in sequence, the problem of choosing a cognitive strategy can be reduced to what's called a sequential decision problem, where the computations we're going to execute are the analog of the actions that we would execute in a traditional sequential decision problem, right? So we've turned this problem into one of making a sequence of decisions about internal computations to execute with the goal of then getting us to the point where we're able to take an intelligent action in the external world. And so as a consequence of formulating the problem in these terms, then we can express this in terms of what's called a meta-level Markov decision process. And we can solve that and in the process derive optimal cognitive strategies using methods that come from the reinforcement learning literature. And so I'm going to spend the next few slides unpacking that and sort of explaining what these terms mean. But the basic idea here is that we have a way of defining this problem of characterizing what an optimal strategy is that when we cast problems in these terms allows us to make use of sort of standard algorithms that we can use for then deriving what the solutions look like. So just to unwrap this a little more, so the basic idea is that when we're thinking about sequential decision problems, when these are just problems that we're making in our environment, that problem of maximizing expected utility becomes one of maximizing the long-run reward that we get by making a sequence of decisions. And the way that that's formalized is in terms of something called a Markov decision process. So in a Markov decision process, we have states of the world. Conditioned in these states, we have actions that we take. And then as a consequence of the action that we take in the previous state we're in, we end up in a new state determined by a transition probability, and we receive a reward. And then from that new state, we take an action, we transition to a new state, we receive a reward, and so on and so on. And so the problem we have to solve in a Markov decision process is to find what's called a policy that tells us for each state what action we should take so that we maximize our long-run rewards. And so that's a problem which can be solved using various kinds of algorithms that have been developed by computer scientists. And so you can take a Markov decision process and then use those algorithms to find out what the optimal policy is and automatically derive what the actions you should take are conditioned on those states. So to turn this into our problem of finding an effective cognitive strategy, we're going to use what are called meta-level Markov decision processes. And in a meta-level Markov decision process, we just make this exact same move I've been talking about, where instead of thinking about making decisions about states of the world and actions in the world, we're now going to make decisions that influence our beliefs, and the actions we're going to take are going to be the computations that are going to have that effect. And so we take our Markov decision process. Instead of states, we have beliefs. Instead of actions, we have computations. Based on a computation that we execute, that's going to change our beliefs. And there's going to be some computational cost which is associated with that computation. And then we repeat this process until we get to some point where we decide we've done enough thinking. We execute a special action. And this action says, I am done. I'm ready to act in the world. And then based on our current beliefs, we take the action that maximizes our expected utility. And so again, the algorithms that we can use for solving the Markov decision process, we can use for solving a meta-level Markov decision process. It's a little tricky. We've sort of developed some better algorithms for doing this. But the basic idea is that once we've formulated a problem in these terms, we can automatically derive from it what the optimal strategies look like. So that's still pretty abstract. What I'm now going to do is give you a couple of examples, which are hopefully going to help this make sense. So the first example, I'm going to focus on a setting which is a classic setting for looking at the cognitive strategies people use in decision making, which is a multi-alternative risky choice task using the mouse lab paradigm. And this is joint work with Paul Kruger, Fred Callaway, Cheyenne Gould, and Falk Leader. And so the setup here is that we give people a choice between different gambles. For each of these gambles, we're going to be drawing some ball, a ball from an urn. We have information about how many balls of different types are in the urns. But what we don't have information about is the payoffs that are associated with each of those outcomes for each of those gambles. But people can easily reveal that information. They just have to click on a particular cell and it provides that information. And so this has been used to look at the strategies people use in decision making because it gives us a way of keeping track of what outcomes people are thinking about when they're trying to make a decision. And so it gives us a way of externalizing those computations that I was talking about and gives us a good sort of first test case for that meta-level Markov decision process framework I was laying out. So to try and ground this in terms of the meta-level Markov decision processes, the idea here is that the belief states that we have are going to correspond to beliefs about what those payoffs might be. The computations we can execute are going to be evaluating a particular outcome for a particular gamble. And then there's going to be some cost associated with this. In this case, this is just the cost of clicking on one of those cells. And then at some point, we've sort of revealed enough of this information. We've evaluated enough options. We're ready to act. We select a gamble, and then we receive a payoff associated with that gamble. And so for a given configuration of this problem defined in terms of the distribution of payoffs, the probabilities associated with the different outcomes, and the costs of clicking, we can then derive what the optimal strategies look like. And so what we did was actually set out to...
Clarification question. So to move between a belief state one to another, is it something that you do, the participant do explicitly? Or so is it like they move from spot to spot, or is it something in their head, like some conceptual belief?
It's moving in their head, yeah. So, and the way that we actually model that, I should say this in terms of our models, is we just model that as a Bayesian inference. So the idea is that by executing the computation, you get some information, and then based on that information, you use Bayesian inference to update your belief distribution. In this case, because we're just revealing the information directly, they start out with a probability distribution over the possible values that might be in that cell. And then once it's observed, that probability distribution just condenses to the particular value that they observed.
Okay, thanks.
Any other questions before I go on here? Okay. So what we decided to do was just to systematically cover the entire space of these mouse lab tasks. So looking at variation in payoffs, so whether the range of payoffs is larger, so the sort of stakes are higher. Looking at different kinds of distributions for the probabilities associated with those payoffs, right? So from something which is very skewed to something which is very uniform, and then looking at different kinds of click costs. And so together, this defines 50 different conditions. In each of those conditions, we generated 20 scenarios. We found the optimal cognitive strategy and let that optimal strategy be executed for that particular scenario. And then what we could do is look at what the patterns are that appear in the kinds of strategies that the model identifies. So the way that I'm going to just show you these results is by taking the pattern of clicks, the sort of states that are evaluated, and putting it into a canonical format. And the way that I'm going to do this is I'm going to make it so that the columns are ordered by the number of times that they were clicked on, and then the rows are likewise ordered by the number of times they were clicked on. So we're going to get this matrix be reordered. So this is the first column, this is the second column, this is the first row, this is the second row. And so that produces a layout that looks like this. And so this gives us a way of canonicalizing across different kinds of click locations and orders and so on. So we're just revealing the strategic information. And then we use that and we apply k-means clustering to the solutions that we see. So when we do that, we find 4 very clear clusters. And so the way that this is being shown, yellow means more clicks, blue means less clicks. And so I'm going to translate these into strategies for you. So these 2 correspond to classic strategies that have been looked at in this task. This is a take the best strategy, where you focus just on the highest probability outcome. And you click it with, you click all the way across that, and then you choose the gamble that has the highest payoff and the highest probability outcome. And then this is what's called the weighted additive strategy, which basically is clicking everywhere and then integrating all of that information. But we also found some new strategies that hadn't previously been identified. This is a kind of satisficing strategy where people focus on the highest probability outcome, but only click across until they see something that's above a threshold, and then they select that gamble. And then this is a hybrid of that satisficing and take the best, where you click across the highest probability outcome. Then you look at the second highest probability, and you do satisficing on that second highest probability outcome. So these are the kinds of strategies that the model identifies, right? These are the sort of optimal strategies for solving these problems. What do people do? Well, we ran about 2,000 participants through this same vast array of mouse lab tasks and performed the same kind of clustering analysis. And this is what we see. So we see strong evidence for the same kinds of strategies being the things that dominate people's behavior, with the addition of this one further strategy, which the model didn't produce, which is just choosing a gamble at random. And I can say a little more about why that happens. Basically, it's because we have some unaccounted for costs in the context of this task, which is that people would prefer to be doing something other than the task. So there's an effective opportunity cost. We can also look at how the different conditions affect the strategies that people use, right? And so this is just showing, as we vary things like the stakes, dispersion of those probabilities, and then the cost of clicking, how that affects strategic choice in the model. And then these are the corresponding proportions in our participants. And so in general, what you can see is that you see the same kinds of trends in the human data as in the model, although humans are less adaptive than they should be. And that's a point that I'll come back to at the end of the talk. But the basic idea here is that you see things like, for example, if the click cost is 0, then the model is always going to click everywhere, whereas people click everywhere more, but less than the model. And again, that's a consequence of there being a higher effective cost for people than for the model here. Okay, so the main thing I want you to take away from this is that we can take this kind of classic problem. It's a very straightforward application of our framework to then derive what optimal strategies look like. We can compare them against human behavior. But as I was saying before, the point of this framework is that it gives us a generalizable model. And that is something where now we should be able to take the same kind of model and use it in other circumstances to make predictions about people's behavior. So I'm going to show you a second example, which is in what on the surface looks like quite a different problem. But in fact, we can analyze using effectively the same kind of model. And so this is joint work with Fred Callaway and Antonio Rangel, looking at applying this approach in the context of a simple choice problem. So this particular simple choice problem is one where you're given a choice between 3 different snack foods, and gaze is tracked while you're making this decision. So you can look at what people are looking at as they're making the choice between these options. And so there's a bunch of, again, classic findings in this setting. For example, people are more likely to look at items that they choose. The items they choose are likely to be the last things that they looked at, and so on. And the way that these results have been accounted for previously is by using things like the attentional drift diffusion model, which is a model where it sort of runs a drift diffusion process, but it accelerates the diffusion in the direction that of the item that you're gazing at, right? But this model doesn't say anything about how you choose what you're looking at. It just sort of says something about the decision process. And we found that using the same kind of model as the one I was talking about before, you can not only capture this decision process, you can also explain the choices that people make about what it is that they're actually looking at. And the way that we set that up is basically by saying, what you've got is these options. Just like in our previous case, you've got some probability distribution. Your beliefs here correspond to the probability distribution that you have over the utilities that are associated with those things, just like the values of the payoffs associated with particular features in our previous task. When you're fixating on something, you're sort of thinking about some attribute of it, and you're getting basically a sample from a distribution that gives you information that you can use to update those beliefs. And so Now you have control over what it is that you look at, what it is that you're sampling from, what information you're getting, and we can formulate that problem in terms of a meta-level Markov decision process in the same way. So now our belief states correspond to these beliefs about the utilities of the items. Our costs correspond again to like a cost for just, fixating on something, gathering information. Here it's just a straightforward opportunity cost. Although we also in this model include a switch cost, which is that when you move a fixation from one item to another, there's a higher cost that's associated with that. And then at the end of the day, when you've got enough information, you're ready to act and you choose the snack food and you receive a reward that's associated with it. And so we can take this model, we can find what the optimal strategy looks like, and then apply it to some classic data from the setting. This is a ternary choice task where you're given these three options. They've previously been rated for how much people like them. And so then we can look at how the choices that they make and the fixations that they make relate to their stated preferences. And so what you find in these tasks, right, as I was saying before, you find this relationship between fixation time and choice. So as people spend more time looking at something, there's a corresponding increase in the probability that they choose it. And the model just produces this phenomenon directly. And the reason why it does this is basically because of the way that you should intelligently gather information in the setting. That if you've got three options, you look at them once, you've gathered some information about each of them, but then if one of them is significantly less good than the others, you're going to focus your subsequent sampling on the two which are better, right? And so you're going to spend more time looking at things that are better because that's more informative to the ultimate decision that you end up making. And that's just something that kind of falls out of the mathematical structure of this problem. So in the same way, you get more fixations for high value items, basically being driven by the same kind of effect where you should be focused on those things which are going to be more likely to be the things you're going to end up choosing, particularly as time goes on, because here you're sort of gathering this initial information and then you're sort of narrowing in on what are the good options over time in a way that increases. And so this very simple model, which is using exactly the same principles as the ones we use in the mouse lab setting, gives us a nice characterization of the data that we see in this setting of simple choice as well. Okay. So when I started out motivating this talk, I talked about, Garry Kasparov being good at efficiently using his cognitive resources and playing chess. So the things I've talked about so far do not look a lot like chess. So I'm going to show you one study that goes sort of one step closer to chess. And that's using the same kind of approach to think about planning. So we developed an extended version of the MATLAB, that's the mouse lab task, which was designed to allow us to look at planning. The basic idea here is that you're helping this little agent navigate through this maze. And the goal is to help the spider here find the path through the maze that has the highest summed payoffs. The catch is, like in the mouse lab setting, you don't actually know what the payoffs are, and you're going to have to click on these cells, basically evaluate these options in order to be able to execute a plan. And this is joint work with Fred Callaway, Bas van Opperston, Cheyenne Gould, Priyam Das, Paul Kruger, and Falk Leader. So in the same way, we can take our meta-level Markov decision process and we can apply it to the setting. And now the beliefs that you have are about the values of the payoffs that are behind those gray dots. And then you have, again, sort of costs for clicking, and the actions that you're taking are clicking on things to evaluate what the payoffs associated with them are. And then at some point, you're ready to act. You take that action, and then you get the payoff that's associated with the path that you select. So what we find in this setting is that when we solve this meta-level Markov decision process and derive the optimal algorithm, that optimal algorithm does a better job of characterizing human planning than basically all of the other algorithms we looked at, which are based on ideas that have been proposed in the AI and computer science literature. So the kinds of search algorithms which are sort of standardly used in AI for planning are things that don't do as good a job of characterizing people's planning in terms of the state that they evaluate as the optimal strategy in that meta-level Markov decision process. And the reason for this is that human planning displays a kind of adaptivity which we don't see in those classic planning models. And just to illustrate this, this is a picture of here on the vertical axis, the best expected value for the best path that you found so far. And then on the horizontal axis, the number of clicks that you've made, the number of nodes that you've evaluated so far. And what you should be able to see here, so blue is low probability of terminating search, yellow is high probability of terminating search. you should be able to see as we go from the bottom left corner to the top right corner, there's an increase in the probability that people terminate search. And so what that's showing is a trade-off between exactly how good is the best solution you found and how much exploration have you done, where if you've already sort of explored a bunch, then you're going to set an appropriate threshold for how good the best thing you found so far has to be for you to stop searching. So people are sensitive to both of these factors, and the optimal solution is likewise sensitive to both of those factors, whereas classic planning algorithms are not. And so this kind of satisfying adaptivity that people display in planning is something that we can capture using this kind of model. So I had again, like, to set this up in terms of I'm going to show you something which is kind of like chess. This particular example was a spider navigating a maze. That's not particularly like chess. And I've used this example as a motivating example for a long time. And I never thought that we'd actually be able to analyze chess as as a case where we can actually look at whether people are efficiently using their cognitive resources. But in the last couple of years, that situation has changed significantly, and it's changed as a consequence of two things. First of all, we have very powerful AI chess engines. And second, we have very large data sets of human chess gameplay that come from online chess platforms. So for example, there's one chess platform that's released all of the games that have been played on that platform. It's a total of about 4 billion games. So it's more data on human decisions than I think any other data set I can imagine. And it's an incredibly rich resource for engaging with these kinds of questions. So the fundamental problem that you have to solve if you want to analyze something like chess, because any chess board configuration is going to be effectively unique. There's this, a huge number of configurations. After the initial part of the game, it's very unlikely that you end up in exactly the same configuration very often. And so what we need to do is have a way of being able to characterize those states in a way that's sort of lower dimensional, or at least allows us to compare against some standard. And so the availability of extremely powerful chess engines makes it possible for us to do that. If we take the answers that those chess engines give us as essentially a sort of proxy for what we should be doing, as a proxy for what the right answer is to the question, we can use that as a way of reducing the dimensionality of this problem and turning it into something that we can actually analyze in the way that we'd like to sort of try and make sense of human decisions. And so we've started to dive into that. And I'll tell you about one project that we've just wrapped up that looks at some questions related to efficient use of cognitive resources in this setting. And this is work with Evan Russick, Dana Costa-Kane, Bas van Opperston, and Marcelo Mutar. And so what we were interested in this setting was whether people do a good job of using their cognitive resources when they're playing chess. Give me 1 second here. And to do that, what we looked at was basically we needed to have a way of defining when you should be thinking. And the way we defined when you should be thinking was by using the fact that chess engines have two modes that they run in. So one mode is like basically providing you with a board evaluation, which is typically at this point, you take a big neural network, you train it on lots of chess games, you train that neural network to predict from the current board position, how likely is it that you're going to win the game effectively. And so that gives you a way of evaluating a current board position. The other way that chess engines then improve upon those initial evaluations is by engaging in planning. So you take your chess engine and you run a planning algorithm, and it can plan out into the future some number of steps, and it can look at what's the quality of the board positions that are reached after that number of steps. And so those two modes that the chess engines can operate in give us a way of defining how useful it is to think, right? If you think about the planning operation that the chess engine engages in as a proxy for human search of future game states, we can ask how useful is it to just sort of look at this board position and act quickly versus to sit down and think about it and try and figure out whether there's a better move that you could make by planning out into the future. And you can actually quantify this for any given board position by looking at the difference between the quality of the moves that result from these two modes of evaluation. So here, this is showing for this board position, there's a big difference in the probability that you end up winning the game based on the moves that you would make if you sort of just do a basic board evaluation versus you engage in planning. So in this case, if you do the basic board evaluation, you would just take this pawn. But in doing so, you would miss the fact that, you know, there's this rook over here that can move over here and check the king, and then the queen can come down, and, you know, there's a checkmate that occurs about 7 moves into the future. And so if you do some planning into the future, you can at least prevent that that checkmate and get back to a point where there's a 50-50 chance of winning the game. And so here there's a big value to engaging in computation. Whereas in this position, it turns out that the best move that you would make based on a superficial evaluation of taking this knight is exactly the same move that you'd make if you planned out 15 steps into the future. It doesn't change what you do. And so there's no extra value to engaging in additional computation here. And so we can measure this quantity. We call it delta UC, the difference in the utility as a consequence of computation, or the value of computation in these for all of the board positions in our data set. And then we can look at how well does this measure the value of computation correlate against how long people spend thinking when they're in those positions. So for each of these games in the chess data set, we have board position, move selected, and how long it took people to select that move. And so when we plot that out, this is what it looks like. So these funny numbers here for the non-chess players are the time conditions that are used in the game. So this is a game where each player has 60 seconds and there's no extra time added after every move. And then these are other variations. This is going up to the case where you've got 30 minutes, and then there's an additional 20 seconds that are added after every move. So this is like a very fast game. This is a very slow game. But what you should be able to see is across all of these different time conditions, as we change the increase in board position advantage as a consequence of expending more computation, you see an increase in the time it takes people to select their move. And so this is showing that people are actually adaptively deciding how to allocate their time when they're playing chess. And I don't have the figure for it here, but one of the other things that we find is that the magnitude of this effect increases as players get better. So one of the things that you learn as you get better at chess is to make better use of those cognitive resources, to do a better job of thinking in the circumstances where thinking is valuable. And so people are internally monitoring and learning how useful it is to think in a particular situation. So the other thing that you might notice when you look at these data is you can see there's a sort of nonlinear relationship here. There's a curve in each of these cases. And so we were kind of puzzled by this. We had initially expected we'd sort of see a linear relationship. We found this very robust nonlinearity. We were trying to figure out where does this come from. And it turns out where it comes from is something which is different from the previous examples I'd shown you about the cost of computation. It actually comes from the particular time cost structure of playing chess. And so I can explain that by just showing you here's some more data. So this is, it looks like something that comes from a model, but this is actually data. There's so much data in this data set, you get things that look like this. What we've done here is bin every one of those board positions into little cells. So there's on each of these plots, there's a little cell that corresponds to the remaining time in the game, and then the board position advantages provided by the chess engine, the probability that you win from that position, irrespective of the time at which that position occurs in the game, as estimated by the model. And so these curves here correspond to the sort of isocontours of, and then what in each of those bins, what we're plotting is the probability that you actually win the game from that combination of board position advantage and time remaining. So, you know, if you've got a good board position advantage, you're likely to win. If you have a bad board position advantage, you're less likely to win. But the importance of board position increases as you start to run out of time, right? So this is, you know, this is as time is decreasing, how good your board position is matters more, right? And so these lines here correspond to the isocontours of win probability in this space of time remaining and board position advantage. So you can actually use this to then work out what the optimal policy should look like in this particular situation. And this is the dimensionality reduction that I was talking about that allows us to actually model behavior in this complex setting of chess. by reducing the problem down to these two dimensions of the time that you have remaining and the board position advantage as estimated by the chess engine, we can then think about each of these situations where you have a choice to make about how much you think in terms of a proposal of a change in how much time you have left versus a change in the utility that you're going to derive from engaging and thinking in that situation. And so the optimal policy is going to be one that says you should only think more if the expected increase in utility is worth it, right? In terms of this, the actual probability that you end up winning the game. And so when we plot out what those isocontours look like, you can see those isocontours have this kind of curvature, and that curvature reflects the fact that as you get towards the end of the game, then thinking more is less worthwhile because you have to have a big increase in board position advantage for any time cost that you're willing to pay. And so when we actually work out what the predictions are that come from those optimal policies, we see the same kind of nonlinearity that we observe in our gameplay data, that people are sort of adaptively taking into account the fact that thinking a lot would bring you closer to the end of the game in a way that is not a linear, doesn't trade off linearly with the increase in board position advantage that results. Okay, so I'm going to wrap up just by running through some of the implications here, right? So first of all, resource rationality gives us a better normative criterion for evaluating human behavior. I'm not claiming people are resource rational. I'm not saying this is a thing that is true of what people do. I'm saying this is a useful tool that we can use for trying to make sense of what people do in these situations. So for example, in our mouse lab setting, we can say, not just, okay, people engage in these different kinds of strategies, but we can say, in fact, the strategies that people are using, while they're the right kind of strategies, they're not using as adaptively as they could be. And we can see that because we can actually work out what the performance is that comes from following that optimal policy that I laid out versus participant performance. And we can actually dive in and we can sort of try and pull apart what those, what the causes are of this gap in performance, right? So people are performing in our data set at about about 70% of the level that they could in terms of solving that problem. And then when we look at what's causing this gap, some of it is higher computational costs. We can take those out. We can kind of come up with a way of addressing that. But most of it is due to using the wrong strategy in a particular situation. So they kind of have the right set of strategies, but they're not quite as adaptive as they should be in terms of using those strategies in the situations where they should be deployed. And so then that suggests a different way of thinking about how you go in and make changes to people's behavior, right? So it's not a matter of trying to teach them sort of classically normative things. It's a matter of saying, giving them some feedback and some guidance about how they're solving that metacognitive problem of deciding what strategies to use. Or alternatively, if we think about the problem here as being one of not having enough computational resources for solving a problem, then another kind of intervention that we can do is to come in and we can give people some extra computational resources. And we can't at the moment put chips inside people's heads, but we can put more computation into the environments that people are in. And that idea of modifying decision environments, people have talked about in the context of nudging, we can actually sort of formally define what nudging is in this kind of a framework, where what we're doing when we're constructing a nudge is we're modifying the costs of these computational actions that people engage in. And then when you express things in those terms, you can think about setting up your nudges in different ways. I'm going to focus on the case where what we want to do is to maximize meta level reward, which is we want to maximize the utility of the actions that people end up with while trying to reduce the cost of thinking that goes into the problems that they're solving. And this is joint work with Fred Callaway and Matt Hardy. And so in our mouse lab setting, we've actually explored simple sort of nudge-like interventions, where what we do is we actually manipulate the computational costs which are involved in revealing particular pieces of information. So we can run the experiment in a way where some pieces of information require 4 clicks to reveal, some require 3, some require 2, some require 1. And by doing that, we're making some pieces of information easier or harder to get. So using our formal framework, we can actually choose to place these higher computational costs on pieces of information that, if people are following the optimal sort of cognitive strategy for choosing what information they get, are going to guide them towards following strategies that are going to use less computation, right? So if we make it harder for you to get this piece of information, maybe you're going to focus on gathering these pieces of information. And our model tells us that that's enough, that it's going to then lead you to end up making the high utility choice in this setting. And so we can actually show that by doing this, by sort of setting up an outer loop of optimization of the decision environment around an inner loop, which is optimization of the strategy within that environment, we can design nudges that reduce the click costs, produce higher payouts, and produce higher overall net earnings for people than just sort of going in and randomly modifying the computational costs that are involved in that particular task. And then the last implication here is that by putting the emphasis back on cognitive processes, right, defining a sort of standard of rationality, which is not just about the actions we take in our environments, but also the internal processes that we should engage in when we're trying to take those actions, and making connections to things like MDPs, it supports a search for mechanisms, either cognitive mechanisms or neural mechanisms that underlie decision-making. And so I think this kind of formal framework is particularly productive for cognitive scientists and neuroscientists who want to understand how human minds and brains work, because it tells us answers to the questions like what people should be doing inside their heads. It gives us a way of deriving what those strategies look like in particular situations. And it gives us a link to a long-standing literature on reinforcement learning, which has both, a lot of behavioral work and a lot of work in neuroscience that tries to identify mechanisms that are involved in solving these kinds of problems in the world, but I think are equally applicable when we think about solving these kinds of problems inside our heads. So thank you very much.
Thank you. This is very interesting. So now it's the time for questions. So those who want to ask questions, just please raise your hand or write it in the chat. Siri, go ahead, please. Go ahead, please.
Yeah, thank you. Super interesting talk. I have two questions. So first off, I think that the Markov process basically says we solve the problem sequentially. Do we know anything about it? Is there any indication say we also solve problems in parallel? And the second question regarding this chess experiment. So basically, we have to form an ex ante judgment regarding how much computation does it take for us, whether it's really worth it to think about it. But this process already involves computation by itself. So how do you think about it?
Great. Okay, good. So my answer to those two questions are actually going to be related. So I can say something about that. So I didn't actually say anything about how I think people are solving that meta level problem, right? The higher level problem. The way that we use resource rationality is just to characterize what those meta level solutions look like. So everything that I showed you showed that people are doing things that are consistent with those optimal solutions, but I didn't talk about, how it is that people could arrive at those. And there's nothing intrinsic to the fact that it's formulated as a sequential decision problem that means that it has to be solved as a sequence of decisions. The object that comes out of the sort of algorithms I was talking about is just a policy, right? And the policy just tells you, you do this in this situation, you do this in this situation, and so on. And so, so when we think about what's going on at that meta level, so in response to your second question, one concern that you could have is that I said, okay, we know that people make mistakes when they're making decisions at the what's called the object level, decisions about the actions they take in the world. Now we're going to try and go back and we'll analyze this and we'll sort of assume rationality at that meta level. Why is that a reasonable assumption when rationality at the object level doesn't work? One reason why I think it's a more reasonable assumption is that the time course is very different at the object level and at the meta level, right? So when you're making a decision, the time course for making a decision is something like seconds, right? Whereas when you're deriving a strategy, the time course for deriving a strategy could be something that's as long as your entire life, right? So there's a much longer time constant on adaptation at the meta level than there is on acting adaptively for, in the context of a single decision about the external world. And for that reason, I think we've got more opportunities to actually develop good strategies at that higher level, because those are strategies that we're going to learn across many individual decisions that we might experience. And so we're then able to construct good heuristics that we're going to use throughout our life across many of the decision-making circumstances that we face. And so the kinds of mechanisms that I can imagine for doing that, one is just explicit deliberation, right? Where you're just sort of thinking, okay, should I do this? Should I do that? Should I do this? I think that's probably not what's going on most of the time. But the other thing that we've looked at is what we call meta-level, or sort of metacognitive reinforcement learning. And so the idea behind metacognitive reinforcement learning is, because you formulated this as an MDP, there's actually two different ways of solving MDPs that people have looked at in the reinforcement learning literature. One is what's called model-based methods, and the other is what's called model-free methods. So model-based methods are more like that deliberative process. It's where you just sort of work out, okay, by planning out into the future, what's the best thing to do? Model-free processes are things that are more like what we think of as traditional reinforcement learning, where you try something, you find out what reward you get, you update your estimate of the reward associated with that action. You keep on doing that through all of the actions that you take. And so the kinds of algorithms that are used for model-free metacognitive reinforcement learning are things, model-free reinforcement learning are things that we can also imagine being used in that metacognitive setting. And so we have a couple of papers where we looked at both of these kinds of things. This model-based rational meta-reasoning, you can actually reduce to a problem of just learning features that are predictive of the outcome of a strategy. For this model-free metacognitive reinforcement learning, what we've looked at is basically providing people with different kinds of feedback. So for example, in our planning task, we give people metacognitive feedback about whether they sort of thought too much or whether they clicked on the right thing when they're exploring the space. And so people, when you give them the right feedback, they learn to plan more in a way that looks like a sort of traditional reinforcement learning, like model-free reinforcement learning setting.
Thank you. Ishan.
Thank you so much for your talk. I love your talk and your work in general. One idea that I find super interesting is this idea of computational cost of thinking. And we've got these complex models of cognition which sort of describe how attention works or how memory works, that attention is spatially localized, or memory sort of has a semantic contiguity, right? So are you thinking of extending your models which sort of draw more on this computational cognitive literature of how these processes are sort of worked out in the human mind?
Yeah, it's not something that I'm planning on doing, but maybe it's something that you're interested in thinking about. But I think the idea here is we're closing the gap between rational action and cognitive psychology in a way that I think allows you to take a lot of the classic insights from cognitive psychology and then express them in a formal framework that then you can use to derive, okay, what do reasonable strategies look like, right? So you could think about that like certain kinds of semantic association might be sort of cheap computationally, right? And so that's a reason why you then engage in those things rather than engaging in deliberation, which is costly, right? I think that's exactly the way that these kinds of frameworks can be cashed out to then generate interesting predictions. And to me, the interesting thing there would be like, if you can then use that to generate predictions about circumstances where people would engage in one mode or another, or sort of switch back and forth or whatever it is, in a way that's more quantitative than I think the way that a lot of the literature currently thinks about those kinds of things.
Thank you.
Yes. Hi. When we introduced you, when Yefim introduced you, I forgot to tell Yefim to say that one of your important achievement was a world champion in choice prediction competition. So you are a member of the team that won our competition. So do it now. But now a tough question that I'm not sure it's easy to answer. In that respect, it's tough. So how do you think is there a clear relationship between this idea, the theory that you're presenting now, and the model that you guys submitted to the choice prediction competition that actually won the competition? Or do you think in the future there will be connections?
So the answer is no. I mean, there's a little bit of a connection with some of the work that we did that was inspired by yours, that was in that science paper, where we looked at how the complexity of the decision problems seem to influence the strategies that people might be using. But it's sort of buried very deep in one of the supplementary appendices. So no, I think about those as things where we have two kinds of models. We have sort of like principled models, and we have effective predictive models. And those two hopefully are going to come together. I think we still have a gap between those. And that's something that, I think is a good challenge for us. The way that I do think this model might be useful in bridging that gap is because the goal here is explicitly to make a generalizable theory. That means that we can then take a new situation and generate predictions about that new situation. The way that in our choice prediction competition submission, one of the things that we did was using pre-training, where we generated data from one of your models, and then we used that to train a neural network model, and then we could then fine-tune that neural network on the limited amount of actual human choice data that we had. So that kind of strategy is one that relies on having good models to start off with. So I think there's a lot of potential there where we can use these principal models to then generate data we can use to train something like a neural network model so that we build a good principled inductive bias into that model, and then we can fine tune it on the limited amounts of choice data that we have. And so at the moment, I think that's the place of convergence, is that this helps us to establish good inductive biases for then generating predictive models. But there's still a gap.
Okay, thanks.
Maria.
This is more like a clarification. Maybe I missed it in the beginning. So when there is a sequence of steps of evaluation, at what point does the person, or in the model, how do you model the last step where there is a decision taken? What is the threshold that decides when the evaluation should stop?
Yeah. So basically, let me go back to this model. That's the thing that the model figures out how to do. So actually, this planning model might be a good example. Okay, so at some point, it's sort of evaluated enough cells and makes a decision to act. And this is what the optimal model produces in terms of these two dimensions of the number of clicks made and the best expected path value. So you can kind of think about this as within that meta-level Markov decision process, there's an optimal stopping problem, right? So the classic sort of optimal stopping problem is something where it's just like you sample one option and you decide you've sampled enough, and then you act, right? You can formulate that as a meta-level Markov decision process, right? You have a belief state, you have an action. In that case, you've only got a single computational action, and then you've done that enough, and then you decide to stop. And so that classic kind of optimal stopping problem is a special case of what the meta-level Markov decision process is doing. What it does, though, is now we can expand that set of actions. And so in our planning problem, the space of actions that you have corresponds to evaluating all of these different cells, right? And so it's kind of like a non-homogeneous version of an optimal stopping problem. And then that's what leads us to this formulation in terms of the meta-level Markov decision process, and then more complex algorithms you have to use in order to solve that.
Okay, and in terms of the behavior or the thinking that this is assumed to model, so how does that thinking work? Is there, or at least according to you, so I am approaching a problem something similar, but more from a psychology perspective, consumer psychology perspective. So, so it's not very clear when we decide that we have made a choice. Is there some kind of internal mechanism for us as consumers to realize when we made a choice? So in a similar manner here, is there an assumption? Is there an assumption of basically when does the person or the individual is thinking and making that choice?
Yeah, so I mean, so the answer is in these more complex models, there's not a simple criterion you can give that looks like that. In the simple choice case, we actually show in the paper that you can derive something that looks a lot like the attentional drift diffusion model as falling out of the optimal policy. So if you're comfortable thinking about things like diffusion models where you diffuse to some threshold and then you take the action based on that threshold, the dynamics are going to look a lot like that. But in the general case of these more complex models, it's just going to be more complicated. But it's sort of intuitively the same kind of thing, that effectively you're trying to accumulate towards some threshold where that threshold depends on how much time you've spent, how much time you have remaining, and and it's the threshold that's expressed in terms of the expected utility that you would derive based on the beliefs that you currently have.
Okay, that is helpful. Thank you. And I missed mentioning anything about myself. So I'm an academic. I'm a professor of marketing. So that's my interest over here. Thanks for that.
Siri.
Yeah, sorry, it's me again. Thanks for answering the previous question. So I think in your model and also in the experiment, it's quite straightforward. What is the state? But in real life, like many situations or decisions involve multiple attributes. So how do you think about this?
Yeah, so I mean, we are explicitly modeling sort of multi-attribute decisions, right? Like you can think about what's going on in this multi-alternative risky choice. We've run alternative versions of this task where instead of this being uncertainty, you just have different features that are weighted differently, right? And then you're finding out about the values associated with those features. So this model generalizes very naturally to a setting where you have multi-attribute decisions. So you can have deterministic multi-attribute decisions where you have feature weights instead of probabilities, and then the same model essentially applies. And we've done a little bit of work modeling those kinds of decisions too. I mean, I think in general, characterizing what constitutes state in a decision is hard. And we've mostly stayed with these sort of laboratory tasks because they allow us to evaluate the ideas behind our models without having to solve those kinds of problems. I think when you start engaging with some of these more realistic examples, like the chess example, right? What we're able to do there is take something which, it's still a discrete game, so there's no continuous structure that we need to be worried about, but we can try and come up with a characterization of state, right, in a way that allows us to then think about what optimal strategies would look like.
Thank you.
Okay, so unfortunately the time is running out. So unless we have any other questions, Tom, I would like to thank you for the great presentation. It was very interesting and thought-provoking. So thank you.
Thanks for having me.
Sure, and see you next time. Thank you.